Hello, wonderful person, this is Anton, and yes, I'm using a webcam finally. This is my webcam that I basically have connected to my computer. Not very good, but that's all I have for now. Anyway, so in today's video, using video games through education, we're going to be talking about something called neural networks. We're actually going to discuss this concept. I'm also going to show you two really awesome simulations that you can then use yourself to teach your computer to do things, or I guess to kind of play a game actually. And we're also going to talk about the very important topic of how video games are used not only in education when it comes to people, but also in when it comes to education of computers. Essentially, video games are actually used today to teach computers to do things. Welcome to What the Math and enjoy this video. And before we start, let's actually briefly discuss what a neural network is. Essentially, the essence of it comes from the brain. So we have neurons in our brain that transmit signals, and using the very same principle, the computer scientists decided to create something called neural networks. Essentially, inputs and outputs that have a bit of a mathematical computation going on in between the input and output that kind of works in a very similar way to a neuron. So let me just show you an illustration so it makes a little bit more sense. And I think the best one I found was actually from this French website right here. And if you don't speak French, it's okay. I'll try to explain it to you. So here we basically have four inputs: capturing of water. I don't know what that means. Capturing of fire, capturing of diamonds, and capturing of center. And then we have four outputs. Either you advance, either you turn right, turn left, fire, or you go back and you correct something. And here I think it refers to the vision, correct the vision. And so we have four simple inputs, four simpler outputs. Now, each of these inputs connects to this part, which is often referred to as the hidden layer. And here, this is where actually all of the math happens. So each of these connects to each one of them. And then each of these connects to one of the second layers. And then each of these will then go into one of the outputs. Now, what happens here is actually very complex math, and I'm not going to explain it to you in this particular video because it does involve quite a lot of calculus. There's actually calculation of derivatives where you have to find the slopes. There's also some really complex graph going on, a bit of linear algebra with matrices, and some of the other more complex matrix related calculations. And all of this is done here, and if you actually want me to explain it one day, I totally will, but it does involve college level math. And then after all of this math is done, it outputs to one of the outputs essentially. So, and what happens afterwards is that, so basically, if this output resulted in a good condition, it will come back and increase the strength of these connections for one of these inner networks. So basically, it's an evolving network that teaches itself how to behave. And this is essentially how, if you ever heard of AlphaGo, and AlphaGo is of course the British computer that was actually able to, or I guess it's Google computer, that was able to beat Lee Sedol, the champion of the game called Go, which for many years was known as an unbeatable game by AI. So there was not a single computer that was actually able to beat a human being because this game is just too unpredictable. But through neural networks, AlphaGo was able to actually learn and beat this guy 4 times and only lost once. But if we had given it one more week, it would never be able to lose another game because it would actually teach itself to always win. And here's actually yet another demonstration or illustration of what's actually happening here. It's slightly simpler than the one I just showed you. So basically you have two inputs, hidden layer where mysterious math happens. This is actually, we refer to this as deep learning. And then there's one output that produces a result. Now, I'm going to post all of these links in the description below so you can actually go through all of these in your free time. And actually one of them even involves, right, this one here, involves building a simple network in 9 lines of Python code. If you actually are familiar with Python, which is a programming language, you can actually try to build your own initial or super basic neural network that will actually teach itself to produce stronger and stronger results. But we're not going to do this here because this is beyond the scope of this video. What we're going to do though is we're going to use 2 specific simulations here, and both of them are neural network simulations, which you can download for free and which you can then try as well. The first one is actually very visual. It's going to demonstrate to you how neural networks work. And it's actually called Sticky Creatures. I'm going to open it up right here so you can actually see what it looks like. It's not a particularly complicated simulation, and I don't think I can make this any bigger, unfortunately, so my apologies for a small screen. But basically here what you do is you teach your creatures, your randomly generated or generated by you creatures, to either jump or walk or basically move around, and their job is to basically learn how to walk really well. And this particular simulation is great because it shows you exactly how your neural network process things. So I'm going to go into settings here. Okay, yeah, that's all good. We're gonna keep it as this for now, just basic settings. And what we are going to choose a creature. You can actually choose from a pre-arranged creatures like this one right here, or you can create your own by basically adding things and creating something that you want. But I think I'm going to go for something that looks ridiculous, like something. That actually kind of looks like a kangaroo. And I kind of like this one right here. It's actually like a little crab thing. Now, we're going to add this. We're going to create this. And we're going to basically make it run simulations. And what it will essentially do is it will learn how to walk through trial and error by constantly predicting a possible output. And then if this output results in a favorable condition, it will go back and correct the strength of the connection, making this more likely to occur. If it results in an unfavorable condition, then it will actually not do anything and continue learning through random selection of random inputs and outputs. So essentially what this computer will do is, let me just start this first. I'm going to start this so you can actually see what's going on. And here's our little crabs. Look at them going on their merry way. So this is the beginning. They basically can barely walk. These guys are going completely wrong direction. Their goal is to essentially reach this way. This is generation 1. This is generation 2. It's learning pretty fast. And you'll notice that it's going to learn really fast. Until at some point, one of these conditions will be so favorable that it will create a super fastly moving creature. Now, let me just disable this for a second. I'm going to turbo this, and we're going to go into display input and outputs. Actually, not this. This, draw neural networks. Now, here is our neural network with inputs, the hidden layer where connections are made, and the outputs. It actually even shows you exactly what's going on here. So here come the inputs, it's learning as it goes, and the outputs put out depending on whether it's favorable or not. So it makes a prediction. It says, okay, maybe this is good. I'm going to try this. It goes through the math calculations. It goes to the output. If it's not good, it will never, or it will do this again, but not as often. But if it's something favorable, if it actually results in a higher score, oh, this poor guy fell down, then it will go back and modify this connection, making it stronger. And this is essentially how our brains work as well. This is how we learn. Even people learn this way, but our brains are way more complicated. There can be up to thousands of inputs per neuron. Each neuron goes through some really complex calculations and then produces an output as well. But this is why we call these neural networks, because they're essentially based on the brain. Now, this is only generation 30. I'm going to be running this for quite a long time, and we're going to come back to this. We're going to actually check it out later, because I want this to go ahead and learn stuff. I'm going to go through Turbo here, and it's going to learn stuff. And actually at generation 50 is going to show me the best representation of this creature up to generation 50. So let's actually wait a little bit and see what it comes up with. And unfortunately I missed 50 by accident, but here comes the generation 100. And it will hopefully show us there we go, look at that. After 100 generations, this is how fast our little crabs can move now. They've learned that you can kind of hop on one leg, you can kind of move around using two legs. They're advancing pretty fast. Alright, so we're going to actually come back to this in a few minutes. I'm going to let it run for a while until we see what basically is created near the end. Meanwhile, let's go into the second simulation I was going to show you, which does involve video games. So, in reality, most of the researchers, and this is actually this is based on a paper that I've been reading that's right here. It's called Evolving Neural Network Controllers for a Team of Self-Organizing Robots. Most of the neural network researchers, basically most of the computer scientists that deal with neural networks, often use video games to teach robots, AI, whatever you want to call it, the artificial intelligence, how to essentially do things, how to behave, and how to create something, or how to modify something, how to essentially become better. So the idea of learning through video games doesn't just apply to human beings, it actually applies to computers. And most of the computers learned to do things through video games. And I'm going to show you how these researchers did it. There's a simulation that they've created called FREVO, and it's absolutely free. You can actually download it from the description below. And oh, wait a second, I already had one running right here. And here is a simulation I ran overnight. It took maybe about 5 hours or so. This was learning or teaching the computer how to play soccer. Now, in the beginning, when you just start, this is what happens. In the beginning, there's actually a few of them I have, and I'm going to actually change this to Germany and Brazil just for fun. The simple game here is basically them just kind of running across the field, kicking the ball once, and just kind of just staying there. They haven't learned anything, they're just trying new things, they have learned absolutely nothing. This was the first simulation. Now, this was after so-called one generation. Let's advance this by about 50 generations, so 50 trials and errors, until they've learned something. So this is what happens after 50. And after 50 generations, you can kind of see that they already started moving a little bit more. Brazil is already getting more aggressive, trying to get the ball, but then they kind of just sort of spread out and make this a wall-like structure, and Germany is just chilling in there, and these guys are just chatting. So that's after 50 generations. It's learned a little bit about how to use the ball, that the ball is actually a good thing, that you shouldn't really just ignore it, and basically they learn that kicking the ball gives you more points. Then at 100 generations, this is what happens. We have Germany and Brazil, and Germany is becoming a little bit more aggressive, Brazil is more defensive, and so they're learning pretty quickly that essentially this is the game where ball really matters, which is why Brazil is holding on to it now, but they're still not really sure exactly what you need to do to actually get the big point, essentially hitting the goal. They're still not sure that this is actually what you need to do. And so through trial and error, because there's so many inputs here and so many outputs, for each player there is directions, there is distance to the ball, there is things like you can kick the ball or you can just run away. There's so many different inputs and outputs that it needs to try them all until it finds out which connections to strengthen. Now this is what happens after 500 generations. And as you can see, I actually have quite a lot of generations because I was writing this for such a long time, but I just want to show you that even after 500 generations, the game becomes a lot more interesting. It's actually something that you can almost call soccer now. So they're going to grab the ball, they're going to pass the ball, they're going to try to take the ball from the other team and essentially go for the other team's goal. They've realized now that you need to try to take the ball here. This is what the game has become about. So you can see Germany is approaching the ball, they're trying to hold on to it, there's a bit of tackling going on there. And so it's essentially looking more and more like actual soccer, maybe like salsa soccer. There's still, some of them are just dancing around, but these guys are chatting again, they're just standing there. So it's a friendly game of soccer between Germany and Brazil, just something they're basically practicing. And over 1,000 generations later, the AI will have learned that basically the game is all about the ball and it's all about kicking the ball toward the other side and trying to avoid the enemy players. And essentially this is now looking more and more like actual soccer. Now it does take a lot of trials and error, it does take a lot of learning on the computer part, but essentially we have now created a simulation of a soccer game. In some of these simulations, you'll have them score the goal, you'll have them actually play a very beautiful game, and they will even develop strategies. As you keep running this, depending on the actual simulation, or not simulation, but depending on the actual mathematical algorithms that you choose, they might or might do this. This is actually because I chose a very simple algorithm. I wanted to kind of finish this quicker. Oh, they might score. Look at that. They might actually score. Oh, so close. That was pretty close. But yeah, depending on the algorithm, they might actually end up winning the game. And that's essentially what it's all about. Now, because this is so complex, it does take many generations. But there's also a very simple game here, a game of Pong. Pong is the game where you have two rackets and there's a ball between them. And in case of Pong, this is how, I'm going to show it to you as well. This is how it all starts. In the beginning, there's two rackets, they have no idea what they're doing, and basically there's a ball that will probably just kind of score every time because they are actually not sure. But this guy just got lucky by accident, so he's learned that you can actually avoid being hit if you hit the ball. So he's learned that pretty quickly. Now look what happens after just 10 generations. This only took basically 10 generations for them to experiment with. And after the 10th generation, they will actually have learned to play this very well, even with 3 balls. Look how good they become. Okay, he missed one, but look what happens within a few seconds here. So within a few seconds, they're actually able to easily manipulate the ball so they never actually miss another one. And this is brilliant. This is because there's not really many inputs here. There's only left and right input for them. And the only output is either you lose a point or you win a point. Because of this, at some point AI will actually find a way to basically always pass these around. Like right now, they will be doing this forever. And this only took 10 tries. They've learned this pretty quickly, and it's really cool how fast they learn. Now, the interesting thing is, if you actually go on YouTube and you look up some of the other game simulations using neural networks, you'll find some incredible stuff. There's actually one of them that I really liked from, I forgot who it was actually, but it was called Mar.io. Mario, but it's Mar.io, like Mario input output. And it's a person who's taught Mario to play the game perfectly. He's actually used neural networks to essentially beat the Mario levels ridiculously fast. There's one for pretty much all major games. Some people just do this because it's interesting. Some people do this to experiment. But essentially, they'll create something like this. Look how beautiful this game is now. And it's essentially Pong played by two artificial intelligences. And this will go on forever. They will probably never miss another ball. They've learned now how to play this game without losing completely, and they'll always have this draw here. And actually, the game is over because the time is finished. Now, in this particular simulation called FREVO, you can actually go through quite a lot of various things. So there's not just Pong, there's also something called Light, there's 2D simulation of drones, there's something that involves cellular growth, I think, or some kind of evolution of a cell. There's mathematical simulations. There's also a way for a computer to try to hold the pendulum without dropping it. And also home energy management system, which is actually the more practical application. This is actually what we're headed toward. When you have so many different tools in your home and they have so much interaction between each other that they need to develop these neural networks to be able to interact efficiently. There's also a racing game, there's another drone game, there's tic-tac-toe, but my favorite is, of course, this simplified robot soccer. So if you actually want to try this by yourself, you click on this, then I like to choose this one because it's a little bit faster. This is a classic evolution. You can choose how many generations it will go on for. I usually choose about 600. Then what kind of a network is it going to use? Is it going to be a simple 3-layer network? Is it going to be something called neat, which is very complex? Or is it going to be a fully meshed net where everything is connected to each other? It's up to you what you choose. This one is a little bit faster, so is this one. And finally, how is the score going to be calculated? And here I think full tournament usually works pretty well. And then you just start this, and it does take quite a while because it does require a lot of computer power, and I think I made a mistake somewhere. There's a mistake here because it's actually giving me a Java mistake. Let's just choose Swiss system, that should work. And so you'll see there's going to be graphs here forming as your computer model actually starts interacting, as it starts going through different generations, which appear right here. And you can always just, click on this button to replay the last generation and just to see what's actually happening to your soccer game. And here, nothing is really going on yet. It will take quite a lot of generations for this computer to learn how to play this game well. Now, if you're actually interested in this particular topic, there is a lot of stuff for you to explore. I would actually recommend reading through this paper, which I'm posting in the description. Also, take a look at these websites I've posted that do talk about how this is going to be the future of computer science, how it's actually really, really cool and important. FREVO is available right here on this page right here. Also, take a look at these Python simulations or Python networks, which are quite easy to reproduce, especially if you're familiar with Python. And possibly even go through them yourself, go through the math that is involved. This is an example of sigmoid function that's usually used in these simulations to calculate the hidden network. There's a bit of a math involved, but this explains to you what the math behind it is. And before we actually finish this video, let's go back to our little spiders. And let's take a look. Look, there's actually 1,000 generations now. Let's take a look at what happens. Let's see how they've evolved over 1,000 generations. Because I would like to see how beautiful and how fast the spider has become after so many generations have passed. And you can actually kind of see that the neural network here has actually sort of changed completely, with most of the focus is being right here. This is the inputs that are really, really strong in terms of connections. And this is what the network has, or neural network has actually learned to do. So a lot of connections right between these points are very, very strong. These ones, not so much. So these are actually useless neurons, or I guess neurons that would eventually become extinct and would probably not be used very much anymore because they're not very needed in this particular simulation. And so this is 1100 generations later, and let's look at our beautiful spider, Mr. Hoppy Jumpy Hop. And this is how fast he's become. So not maybe as fast as I hoped he would, but he is pretty fast. And if I actually keep running this for, you know, for a few hours, as it reaches 10,000, 15,000 generations, it will become ridiculously efficient. It will become so efficient that it will run faster than any other creature that we have in our real world. But this is also how evolution works as well. This is actually a very good biological model of evolution and how it sort of uses trial and error to come up with the perfectly fit creatures. Anyway, so hopefully you enjoyed this video and hopefully you learned something from it. Let's actually take a look at these guys as they sort of run around, compete with each other for the best, most fit crab in the world. And essentially give this a try. I'm posting the link for both of these in the description below. It's super fun to play with, it's super fun to learn about, and this is actually a very sort of direct application of high school math to programming, to coding, to real life in a sense, that might become future for us relatively soon, because neural networks are becoming part of our daily lives and they're basically going to be everywhere soon. Just wait a few more years and neural networks are going to be in every single house. Anyway, thank you so much for watching, everyone. I really hope you enjoyed this video, and if you did, click that like button, possibly subscribe, and maybe share this video with someone who you think likes video games, likes learning, and also likes math, science, space science, anything really. Anyway, I'll see you guys in the next video. Game you later, and as always, bye-bye. Oh, and by the way, if you actually know of some other simulation that has neural network video game learning, or something that you can see on the screen right now, and I haven't mentioned it in this video, please post it in the comments below so we can actually take a look at this together in one of the future videos where I may actually explain to you the math behind this as well. Anyway, thank you so much for watching. Bye-bye.